I think we've got a fairly steady number, so we'll start things going. Welcome, everybody. Thank you all for joining. This is the first of our Energy Insights events from the Royal Meteorological Society, entitled Lessons for the Future, ensuring that the future grid is resilient in the face of climate change. We've got 4 really good speakers for you today, and we've got further events coming up later in the year as well that I'll mention later. Just a bit of housekeeping beforehand for those of you that are here. So if you are on the Zoom link, if you are having trouble at the moment seeing it, there's a couple of things we'll go through with Zoom to do so. First off, we're going to have the 4 talks. There'll be about 20 minutes each, and then at the end of the 4 talks, we'll have a question and answer session. If you wish to ask a question, everybody is muted in here, so you'll see a Q&A box on the side. If you click that, you'll be able to not only type in your own question, but you'll also be able to upvote any questions that anyone else has asked. If you see a question that you want to know the answer to, then feel free to upvote it, and we can then sort them by those that are the most sort of poignant questions as we go through. If you are having trouble seeing us or seeing my slides as they are at the moment, then the easiest way to try and make them bigger is to just close the chat off, close that, and there's a little button in the corner for enlarging the screen. We know that sometimes with Zoom as well, if you're watching on the browser, you can sometimes have some difficulties if you're not using one of the main ones. So if you are having trouble, feel free to log back in using Chrome, Firefox, Safari or Edge. All should be without issue, we hope. For those of you that are unaware of what the RMETS is and what we do, the RMETS is an organisation that helps promote meteorology and climate-based work around the country. In terms of what we do with the energy sector, we have a small team that works, and we do things like training. We have various events throughout the year, networking opportunities, various other sort of things as well. We do have a special interest group and a mailing list. The special interest group meets 3 times a year, and it's made up of people from academia, industry, consultancies, and sort of NGOs, all those kind of things. If you are interested in that, please send me an email at james.mollard@ed.ac.uk. But if you're just interested in signing up for our mailing list, or finding out more about what we are doing throughout the year, then you can look at the RMETS website with the link there at the bottom. If you're not yet a member of the Royal Meteorological Society, then please do consider joining. There are lots of benefits that you get as part of your membership. These include access to journals, publications. We have various lectures and training courses that you can do on them. There's also access if you're an early career researcher for mentoring, and multiple events that are not just online. We also have the local centres around the country which host monthly or bi-monthly events with speakers that come from all over on all different kinds of topics. And it's a really good place to be a member of, and it is really useful to those who are in any way interested or working with weather, climate, or any kind of meteorological data or work. So our programme for this afternoon, we have 4 talks. We'll start off with Colin and Sean from Newcastle University. We've then got Daniel Donaldson from the University of Birmingham, Gruff Edwards from TNEI Consultancy, and then Paola and James from the UK Met Office. As I say, those will run for about 20 minutes each, and then at the end I'll invite all the speakers back in, and we'll have a Q&A session in which they will be able to answer any of your questions that you've got for them. That should take us through to coming up towards 4 o'clock when we'll close the meeting. So there'll be no questions after each talk, but save your questions and put them in for the end of the session. And then finally, I mentioned we've got some further upcoming events. The second one of these talks, these Energy Insight events, is coming up on the 23rd of April between 2 and 4. This is lessons from the future. For the future, the second one is going to be looking at lessons from the past and how the energy sector has learnt some lessons from previous weather events, whether they be storms, Dunkelflaut, or anything that's happened previously. So we're just finalising the exact list of speakers for that, but you can already register for that event, which will get you access to seeing the updates when they come through. And also a QR code there for if you want to see any of the other RMETS events, so whether that be your local centre meetings or some of the other work we do with other groups such as insurance, forecasting, long-term climate change, any of those ones, they're all there on the RMET website. So without further ado, I'm going to pass over to our first speakers. Colin, are you there and able to hear us?
Hi, James. I'm here.
Perfect. Thank you very much. I will allow you to introduce yourself and your work. If you're able to share your screen, it is all yours.
Yeah, okay. Can you see that?
Yep, that's perfect.
Yeah, brilliant.
Excellent.
Okay,
Thank you.
yeah, thanks. Great. Thanks, James, and thanks you and Ormets for the invitation to come and speak today. My name is Colin Manning. I'm a postdoc at Newcastle University, but I'm based in the UK Met Office within the High Resolution Climate Modelling team. Today, I'm going to speak about some of the work that we've been doing about trying to enable evidence-based climate resilience strategies for electricity networks. And so the basic motivation behind this, and I guess are the well-known issues facing challenges facing the energy industry, stem from these converging pressures of climate change and decarbonisation. So to reach net zero by 2050, firstly, we'll see more weather-dependent generation, but also we'll see the electrification of key sectors. So this will include electrified transport, domestic heating, and industry. And so alongside this, we're seeing changes in our climate. So climate models are projecting increasing risks from heat waves, flooding, and windstorms, which are all important drivers of power outages within the UK. And so taken all together, the increased risks from the hazards and climate, as well as the electrification of key sectors, will, one, increase the risk of large-scale power outages occurring, but also it will create greater consequences from a larger societal dependence on this infrastructure. So the question that we've been trying to answer is how we can use weather and climate data to better enable preparation for these future risks. And so the way that we've been doing this follows these kind of two steps here. So firstly, we're trying to improve knowledge on weather-driven risks and how we can mitigate them. And so we're involved in the CS Now project, which involved running interviews with utility operators from both gas and electricity networks. And we were trying to understand the weather and climate risks or their understanding of them in terms of the types of hazards and combinations of hazards that affect which hazards assets that they affect, as well as what options that they have available to mitigate these risks and the resilience strategies that they already apply. Then secondly, we've been developing quantitative frameworks for climate stress testing. So these include impact models to predict power outages due to various hazards, such as windstorms, and also using these to run cost-benefit assessments of a given resilience strategy. And we also want to use this then to identify the robustness of these resilience strategies across different climate scenarios. So from all of the interviews, we tried to summarize the information that we gained within using a conceptual model. So here I present a conceptual model of a power outage event. So each arrow that you see here is a causal pathway from one thing to another. So for a power outage event, when it begins, it starts with a hazard that we're terming an infrastructure hazard. So this might be a windstorm, it could be flooding or heat waves that cause failure of a network assets. And if there's no redundancy in the system in order to continue the supply via another route, then this will result in a supply disruption. At this point, the emergency response will kick in. And so under normal conditions, we might expect recovery to be achieved by time at T1 here. But it can happen that in adverse conditions, this expected recovery time can be put out to time T2. And the reasons for this is that we have these many, what we would term response hazards. So we could have persistent winds after the initial damage, or we could have heavy rainfall after the initial damage. And this creates quite difficult conditions for the responders themselves who are out there trying to fix the problems. We might also have flooded roads, or we could have roads that are covered in snow and ice, which also creates difficulties in actually reaching the place where they need to get to. And on top of that, if we have critical infrastructure that's linked, that needs electricity, such as telecoms, then outages in electricity can lead into telecoms outages, which creates difficulties for remote workers to communicate with the network centers. And so altogether, this inhibits the emergency response and prolongs the outage. So what's important to note here as well is that each of these causal pathways and arrows represent intervention points for a resilient strategy or adaptation options. So these strategies might include upgrading your infrastructure or increasing your network redundancy so that if a hazard does occur, it either stops the failure from occurring in the first place, or if there's enough redundancy, it doesn't result in a supply disruption. We can also improve emergency response, or we can increase the monitoring in order to identify areas of the network that need improving before they fail, as well as improving the resilience of interdependent infrastructure. For instance, if roads are more likely to flood, can we improve things like drainage, which will prevent the flooding occurring happening on the road, and so therefore people won't be inhibited in getting to where they need to get to. So this conceptual model also summarizes how we're thinking about stress testing in general, and that we need to have a quantitative approach where we can model the relationship between infrastructure and the impact, but also be able to quantitatively intervene within the model to assess the effect of any adaptation strategy and how that might impact the future projections of a given impact and so on. So I'll go into this in a bit more detail. So for the climate stress testing, I'm going to present work that we've done mainly for windstorms. And we've developed a statistical model which is calibrated with local district level information. So here we're working within the national grid electricity distribution networks. And these are 36 districts in total, and you can see the boundaries between them across these regions here. For data sets, we have a 2.2 kilometer hindcast, and this is downscaling error interim data. And we have this between 2001 to 2019. And this gives us 3 hourly wind gust time series for each of the district areas. And we're only considering the extended winter season, which is from October to March. We're following a storm event-based approach. So we've identified storms using cyclone tracks. And then for each of those storms, we have 2 metrics. One is the maximum wind intensity per storm, and the other is the number of faults per storm. So we're basically predicting the number of faults per storm based on wind intensity only. Okay, so I won't go into too much detail about the statistical model. There's a couple of steps in order to produce these predictions. But in general, it's based only on wind speed only. And it's a 2-step approach, which we're producing seasonal predictions. So firstly, we have the model that simulates the expected damage of individual storms. So we produce that prediction for each storm. And then we take the simulated damage of each storm and we accumulate this seasonally. We don't do this for events only because we can see here within this XY scatter plot that there's quite a lot of dispersion when we're using only wind speed to predict this. So over a longer time scales, we can start to average out the random effects from different contributing factors across the whole distribution here. But yeah, these plots on the right show the performance of the seasonal predictions. On the right for four of the regions across the NGED network. So South Wales, East Midlands, West Midlands, and the Southwest. So yeah, the time is on the x-axis, and we have the number of faults on the y-axis. So the observed seasonal accumulations are represented at the red line, and the predicted are represented with the black line. So you can see that generally the year-to-year variability is captured quite well within the model, and the magnitude of the seasonal accumulations is also captured quite well. There are cases such as these Midlands where we're kind of missing out, and there may be reasons for this within the data set that we're using that we have to look into. But in general, we're quite pleased with the results that this approach is obtaining. It's quite a simple approach, and we're quite, this provides like the basis for the stress testing that we're going to do. So we're now bringing in the climate projections. So we are using the UK climate projections, UKCP. And these simulations follow the RCP 8.5 scenario. So it's a high emissions greenhouse gas emissions scenario. We're using the convection permitting model over the UK, which is a 2.2 kilometer resolution model within this domain. And this downscales global information to this 2.2 kilometer resolution. One thing to point out is the model that we're using, the climate model that's used here, is quite similar to the hindcasts that produced our observed wind time series. So this consistency between the data set that's used to calibrate the impact model and the data set that's used to produce, or the model that's used to produce the climate time series, helps us to minimize any errors between the two types of data sets, and remove any need for bias correction, at least in theory. So this is a 12-member ensemble, and this is designed to capture a wide range of possible climate scenarios and outcomes. So we have 12 100-year simulations. So these each represent 12 possible pathways of how climate may develop over the 100 years. When we're applying the impact model to climate projections, we follow this workflow. So firstly, within our climate model output, we identify the storm events in each of the simulations. And for each storm, then we identify the maximum wind gust intensity. This is then used as input into the impact model that's calibrated on observed data. So we get a prediction of damage for each storm, and then we also accumulate this seasonally. So in the end, then we have climate projections of simulated faults. So we have 12 100-year time series of the seasonal electricity faults. And this is what the results look like. So each panel here is one of the climate model members. We have the x-axis is a timeline, so from 1980 to 2080, and then on the y-axis is the number of faults. The black line is the historical faults, and this is just to give an idea of a comparison of the variability and type of magnitude that we've seen in the historical period. We don't compare the actual temporal sequencing of the events because this doesn't make sense, because the climate models are not receiving any observed information. So yeah, there's two things that I'd like to point out here. One is that across the ensemble, there's quite large differences, both in the magnitude and seasonal variability. So if we compare the blue in panel B with the pink in panel E, we can see the blue is quite like low seasonal year-to-year variability. And generally the peaks are almost always below what we've seen in the observations, but for one at the very end. Whereas in this panel E, for the pink member, we can see that the variability is actually quite high, and we're seeing a lot of events that are much higher magnitude than anything we've seen in the observations. So the second thing I'd like to point out is this, like, that's extreme seasons in climate simulations, and that the climate model is producing simulated damages that are far in exceedance of anything that we've experienced, at least during this 10-year historical period. So yeah, what can we do with this, and how can we actually use this to aid any decision making? The first thing that we can do is try and quantify a cost benefit of a proposed resilience strategy. And the second thing we can do is, given that maybe the cost benefit or the resilience strategy is seen to be cost effective, we can assess its robustness across the ensemble. So are there cases or single years in which the resilience strategy may fail? Maybe there's risks that we just can't tolerate. And so can we then develop other strategies that we can use to mitigate the impacts if such an event were to occur, if we can't actually fully engineer against it to prevent it happening? So firstly, start with the cost benefit analysis. So this is like a counterfactual scenario from climate projections. The workflow I have here is what I have for the producing the time series on the previous figures or previous slides. So we have our climate model output that goes through our impact model based on observed data, and this gives us the climate projections. And these are climate projections based on historical vulnerability of the networks. So it's assuming that the vulnerability of the network won't change in the future. So we can term this type of do nothing scenario. And we can bring in a different scenario, which is an adaptation, where we apply an adaptation strategy. And we're doing something quite simple here. We're not coming up with an actual resilience strategy. We're just trying to demonstrate how it might work. So we assume a strategy reduces an expected damage by X%. And so this means that the historical damages, or it's kind of a counterfactual scenario where it would be the historical damages that would not have occurred following this strategy. And so, yeah, we put the predicted damage from the climate models through this adaptation strategy, and then we get this investment scenario where we have the climate projections with an adaptation strategy applied. So it's quite a simple scenario. This is specifically what I've done is to assume a percentage improvement over time. So for instance, say in 2026, we have a large investment, which achieves a 10% reduction in any predicted number of faults. And then after that, every 4 years from 2030 onwards, we have a further 2% reduction. So for instance, in 2026, we would predict the faults, and then we would the resultant faults would be 90% of the predicted faults. And then after that, it would be maybe 88.2%, 86.44%. And over time, these savings, I guess, accumulate to about 66% of the predicted faults. And this is what applying this strategy might look like. So this will be the difference between the investment scenario as compared to the do nothing scenario. So on the x-axis is the timeline. So we can see that there's no difference up to 2026. So this is when our investment begins. And then the total saved faults, which is the cumulated difference between the two scenarios, the investment scenario and the do nothing scenario over time. So yeah, these results are demonstrative. It's an idealized scenario where the resilience strategy achieves an assumed number of fault savings or percentage fault savings. But certain things that we can point out from doing this is that savings will compound over time. So we get much greater, can compound over time, and we can estimate the likely time of return on investments. So people might be interested in getting a return in the next 4 years, but I mean, we can use the climate models to assess whether or not that kind of saving in that amount of time or that return on the investment in that amount of time is actually realistic or not. And also we can see that the uncertainty in investment across the ensemble grows with time. So we can see that the differences between them in 2040 is much smaller than the differences in 2080. And this is due to differences maybe in their climatologies across the members, as well as the differences in future changes in those members. So of course, this is quite an idealistic scenario. I guess for more realistic analysis, we might think about the type of assets that are failing and the likely costs of repairs, as well as the cost of the actual investment that's achieving the savings. And then we might think of the duration of outages to estimate the likely customer payouts, which is measured in customer minutes lost. And then thinking about more realistic targeted resilience strategies. And this is something that we'd have to co-develop. This is certainly not something within the scientific community that we could do. We'd have to have, I guess, policymakers and the stakeholders on board. So the second thing that we can look at then, so we might assume that our given resilience strategy is cost effective and so on. But also we need to check whether it will be robust across the ensemble. And we don't know what the most likely scenario is, and we certainly can't engineer for every possibility. So we could end up with one scenario, such as the blue line here, where we have variability that's similar to what we've observed, and we don't really see a whole lot of change in the future. Or we could have this member of that's shown by the pink line, where the variability is much greater in this member, as well as the magnitude of type of extremes that we're likely to see will both increase in frequency in the future and will also be much higher in magnitude than anything we've experienced. So we can start to use the ensemble to identify these cases and develop storylines, I guess, of these very extreme years in the climate simulations to firstly try and understand the plausibility of them. Are they actually likely to occur? Are they possible to occur? And then we can look at the temporal sequencing of these events and try to work out, based on lived experience of past events, understand how emergency response might actually deal with these and try to understand how we can mitigate the worst impacts and certainly the cascading effects that might occur from them. Okay. So besides that, I think this is all based on wind speed alone. We've done some work looking at the other contributing factors to wind-driven power outages, and it's well known that the winds from anomalous directions, or when occurring over wet soils or when trees are in leaf, that wind-driven power outages can be amplified in these conditions, mainly related to increasing the probability of trees falling on overhead lines, which is the main cause of power outage or damages to infrastructure in windstorms. So these effects might need to be taken into account to get more accurate depiction of what might happen in the future. We certainly are confident that there will be wetter winters and possible that there'll be longer growing seasons as well, such that we might get a growing interaction between the storm season and growing seasons as well. So that work is published. Besides that, we've shown work for windstorms, and we've also done work for other hazards that are important for electricity networks, such as heat waves, wet spells, and cold spells. And this is done during the accelerated project. And so, yeah, we will need to kind of consider these in order to understand how we would prioritize investment across different hazards. Certainly, when we look into the future, we can see that windstorms, as we've seen with the previous results, that there's quite a lot of uncertainty in the windstorm projections across these three time slices. So from 1980 to 2020, or 2030s time, and the 2070s time. But for wet spells and hot spells, we certainly are quite confident that we will see more intense heat waves and wetter winters, more flooding, and so on. Okay, so I'll leave it there. And just to conclude that we've developed a quantitative framework for climate stress testing in electricity networks. And there's more work to be done around different hazards, I think. And further development modeling capabilities are needed as well, in terms of improving predictions for individual event damages by including these multivariate effects, as well as development of actual adaptation strategies that can be used for input. As well as understanding how the electricity networks will actually change in the future, and how we can embed that into the stress testing framework. But yeah, if you need any more information, we have a couple of reports that are published online, as well as some publications from previous projects. So yeah, thanks so much for your attention.
Perfect. Thank you very much indeed, Colin. As I said, if you've got any questions for Colin or for Sean, who's also here from Newcastle as well, please put them in the Q&A box at the bottom. I see there's a couple in there already, which is good to go. And they will answer these at the end of the session in our Q&A section. So yeah, thank you again, Colin. I'll now ask Daniel Donaldson from the University of Birmingham, who's going to give us an overview of the climate change risks to the UK energy infrastructure. You're on mute, Daniel.
There you go. Wouldn't be a presentation without it. So, hello, my name is Daniel Donaldson. I'm an assistant.
We've got you on presenter view, Daniel. Rather than
share the full view. Great. Can you see the full view now?
Yep, that's perfect. Thank you.
Great, thank you. My name is Daniel Donaldson. I'm an assistant professor at University of Birmingham and deputy head of our Resilient Systems and Climate Action Research Group. And today I'll be presenting a brief overview of some climate change risks to the UK energy infrastructure, taking a perspective of the ongoing climate change risk assessment. I've been part of a consortia that's been drafting the technical report that's part of that risk assessment, and the presentation will help frame some of the thinking around adaptation and climate change risks here in the UK. So if we look at adaptation risks and risks to climate change in the UK, it's important to start with the transformation to our UK energy networks. So if we look out what risks are we anticipating in the future, I want to start with how we've seen the networks change over time in the decades that have come before. So if we look all the way back to the 1950s, we can see one of the prior transformations where in roughly 12 years, we see 4,000 miles of new transmission construction to form at the time what was the supergrid and now the backbone of our modern infrastructure here in the UK. So 12 years, 4,000 miles. We then go to the 60s and 70s, and we can see similar transformation of our gas transportation network. So millions of homes and users kind of switched from town gas to natural gas over the 60s and 70s. And if we progress forward, we can see in the 1990s, this dash for gas, where we see 40 gas-fired power stations built over a similar time frame, really showing from one period to the next these big changes in both the electricity transmission, our gas infrastructure, and then also our electricity supply. And as we look to see kind of closer to the current age, we can look no further than National Grid and their Great Grid Upgrade program, where National Grid is investing over £30 billion over the period from 2025 to 2029 to ensure access to clean and secure energy. And what we'll see is, going all the way back, we see these big shifts, these big transformations that have happened. And when we look at particular infrastructure, we want to make sure that infrastructure is resilient, secure, for not just today's period, but also the kind of futures that Colin was talking about just now, looking out, 2080 and beyond. Now, that gives a bit of context from the infrastructure itself. But when you look at the supply and demand of our energy sector here in the UK, using kind of the clean pathway from the seventh carbon budget, or the balanced pathway from the seventh carbon budget, we can see in 2025 roughly 280 terawatt hours of demand. We then see onshore and offshore wind, kind of 16, 17 gigawatts, solar 20 gigawatts, battery storage 7 gigawatts, 10 gigawatt hours. And if we look all the way out to 2050, we'll see significant transformation there. So projected demand more than doubling. We see offshore and onshore wind, onshore growing to 37 gigawatts, offshore 125, five-fold increase in solar capacity, and a significant growth in battery storage as well. So not only are we seeing big upgrades on the transmission, the electricity side, we're also seeing drastic changes in demand and supply forecast as well going out to 2050 and beyond. So if we then look at that in the context of the climate change risks that our energy sector might face, the UK has quite a robust process to evaluate those risks. And if we look in the Climate Change Act of 2008, there was a 5-year process that was set out in that act that governs and outlines the process for both adaptation policy, but the assessment of risk as well here in the UK. So one of those measures is through the Climate Change Risk Assessment, CCRA. So this aims to set out the challenges and opportunities for the UK under a changing climate. We see different sectors captured in that, whether it's health, the built environment, infrastructure, economy, land, nature, and food. All of these different sectors being evaluated for the risks and opportunities that are presented by climate change. We then look at the National Adaptation Plan, which then sets out how the UK adapts to that changing climate, and then ongoing adaptation reports that are filed under the adaptation reporting power that looks at how organizations respond to those challenges and opportunities of climate change. And on the figure on the right, you'll see that cyclical fashion where climate projections and research, such as that presented by Colin and Sean earlier, feed into the picture. We then see adaptation reporting from those institutions. We then see government policies, regional sectoral plans, all feeding into the cyclical process on the assessment of climate change risks and adaptation. And if we look from an adaptation reporting perspective, for context, the third round was in 2021, the fourth round in 2024, and CCRA4 is underway as we speak. So I'm going to start briefly with the adaptation reporting portion of this. And if we go all the way back 2009 to 2012, we saw the first round of adaptation reporting where 91 organizations were mandated to respond, and a further 13 were then voluntarily invited to submit their adaptation reports. We saw over 20 of those reports come from the energy sector. You can see an overview evaluation back in 2012 from Cranfield of that. But roughly every 5 years, we then see another round of those adaptation reports. So if we looked at the second round of reporting, you'll see from 2013 to 2016, we see DEFRA asking for progress updates from those organizations, along with a further 11 that are invited to report there as well. And on the right-hand side, you can see a breakdown of those reports by sector. And as we're looking at energy in the energy sector today, I'd like to draw your attention to particularly electricity generators, transmission and distribution, as well as gas transportation. So these three sectors, you can see strong participation in both rounds of the reporting to that point, with electricity transmission and distribution really being higher than any of those other sectors as far as number of reporting organizations. Now, if we then move to ARP3, which is much more recent, back in 2021, you'll see continued progression across those similar sectors with energy generation, electricity transmission and distribution, and gas still continuing to provide a robust reporting of adaptation. And most recently, ARP4 in December 2024, where there was a prescribed set of climate scenarios. And again, roughly 20 different energy sector organizations filed reports tracking both the progress and response to these different climate change risks. So if we look at those adaptation risks, or those adaptation reports, filed to inform this whole process, those ARP reports inform the UK's climate change risk assessment. And CCRA4, as I mentioned, is underway at the moment. And a key part of the climate change risk assessment, CCRA4, is this independent assessment technical report. And the independent assessment technical report is written for the Climate Change Committee and underpins the CCRA that occurs every 5 years as mandated by that Climate Change Act. And the main end users of this are government policymakers. So this reviews those risks and opportunities to climate change. And the last technical report for CCRA 3 was published back in 2021. So again, 5 years after that, we're anticipating the next technical report to be published later this year in 2026. And the technical report then is building on all that information, that's building on all the evidence that's taken place in those last 5 years to inform these different structures of both adaptation and policy and government policymakers as well. So if we look a little bit more at CCRA4, we can see the time periods of interest across the assessment are looking at the present day, so what the risks and opportunities from the range of possible weather and climate conditions are at present, and then looking out across 3 different time horizons. So looking out to the 2030s, to look at, okay, what is this next round of national adaptation programs? What should they be preparing for? Looking out to more of a mid-century reference period that's looking at this a bit of the longer term, regardless of the trajectory of greenhouse gas emissions, and then looking out to a late century reference in the 2080s, where we can look at the implications of further climate change, particularly for long-lived assets such as infrastructure. So across those different time periods, there are different climate scenarios that are being considered. So if we look back to that 2024 proposed methodology, we can see the different climate scenarios of interest. So again, for those time periods, we see in the 2030s, a prescribed global warming level out to the 2050s as well. So central was 1.5 degrees Celsius and 2 degrees Celsius in 2030s and 2050s. And then a high climate hazard looked at 2 degrees in 2030s and 2.5 degrees in the 2050s. And on the right, you can see how that extends further out into the 2080s and 2100 time period as well. seeing that increase in global warming level, and then the implications on that for both climate hazards as well as these different sectors. Now, if we look across what sectors we're talking about today, I'm going to focus particularly on the infrastructure sector. And CCRA3, so the previous climate change risk assessment, had 13 different risks in the infrastructure sector. And what you'll notice is there's a mix across those risks between those that are focused by a particular sector. So in this case, there was risks to bridges and pipelines. So those specific types of infrastructure from flooding and erosion, or risks to offshore infrastructure from storms and waves. And so you can see both a mix of risks grouped by particular infrastructure sectors, or risks that were more grouped broadly by the type of hazard. So we could see infrastructure services from river and surface water flooding, or coastal flooding and erosion. But overall, there were 13 different risks that were considered, a number of which directly affected the energy sector. Now, the approach in CCRA4 has shifted slightly to split the risks instead of across these groupings. Now the risks are being split by sector. So there were 10 different overall infrastructure risks. The first one focused on interdependencies across sectors. And then 3 specific risks were associated with the energy sector itself. So we have risks to electricity generation, risks to electricity transmission and distribution, and risks to fuel supply systems. And so each of these sections within the infrastructure part of the technical report go into detail on what risks across all the range of hazards are associated with, in this case, electricity generation or fuel supply or T&D assets. And the process to gather that information has been, again, over a long period of time, doing first a literature review of academic and non-academic literature published over that 5-year period. There were then multiple calls for evidence issued where, whether it's researchers, independent organizations, stakeholders could all submit evidence into 2 different requests window for consideration in the report. And then there was a number of different stakeholder engagement activities. So there were surveys sent out to the infrastructure sector. There were interviews and conversations. There was meetings with groups like the Infrastructure Operators Adaptation Forum, as well as a Met Office Academic Partnership Energy and Climate Strategic Forum that focused on infrastructure. And all of these means were ways of engaging, collecting information and evidence to inform the technical report. Now, there were also presentations to the NAP risk holders, as they'll be recipients and engaged in the process, both in the evidence gathering, but also the implications beyond. And there was also an open community review that took place just last December, where a draft version of the report was published for community review. And anyone and everyone was invited in that open community review to then submit feedback and comments on the report through that process. So all of this was a means to gather evidence to inform what are the risks across the sector for particularly the energy, looking across generation, transmission distribution, and fuel supply systems as we anticipate the climate changing and changes to our infrastructure systems. So I'm going to give just a brief example of some research that we've been doing at University of Birmingham on a specific hazard before ending with some conclusions from my own reflections over the process of CCRA4. So if we look particularly at wildfire is an emerging area of threat here in the UK. It probably is not the first one that would come to mind when you think about the hazards we face, particularly our energy infrastructure here in the UK. But it's one that we've been looking at as we anticipate this risk to continue to change in a future climate. So what we've done at University of Birmingham is we've started with field work. So as part of a separate project, there was called the UK or Towards the UK Fire Danger Rating System. There's been some great field work carried out by researchers here at University of Birmingham to look at how do we anticipate and how do we understand the characteristics of our natural environment, and how does that then influence the fire behavior if a fire breaks out? So what you'll see is some samples of that field work. One of the efforts was to collect sample data from all over the UK, a great fuel moisture survey to look at informing some of these characteristics of wildfires, particularly here in the UK. And what that's enabled us to do is develop a wildfire model that captures the changing vegetation, the changing influences of season, of live fuel moisture, of the impact of slopes and slope angles and weather, and use that to better model what we anticipate would happen or the behavior if a fire were to break out in a particular area around our energy infrastructure. And you may be saying, well, do we really even have any issues with wildfires? Do wildfires pose any threat to infrastructure here in the UK? I recognize other places around the world, but we've heard, warmer, wetter winters. Is this really something that we need to be thinking about? So first, I'd like to highlight, this is an example of, you'll see a transmission line in the Wareham Forest, where a fire burned under that transmission line, showing that we do get fires that interact or intersect with our energy infrastructure here in the UK. But what this led us to do is really look at, well, how often does this occur? What might be the characteristics of those fires, and where might those fires be located? And really, how is this changing with the changing climate? So we've built on this wildfire model with fieldwork parameterized assumptions to then take a spatial overlay of land cover, of topography, of weather, to look at the vegetation, the season, the fuel moisture aspects around the country. And then we've used that particularly for England, but also in other parts of the UK, to look at how might fires change with climate and how might those affect our infrastructure. So what I'll show you on the right is a figure that illustrates the changing flame lengths in both spatially and in different climate scenarios across the UK. So the top figure shows the yellow, or the brighter color, is a higher increase in flame length if a fire were to break out in those areas. And so what we see is a huge change, in this case, up to 700% increase in flame lengths. And that's governed by the underlying aggregate classes, so the type of land cover in those locations. So what you'll see is under current conditions, we see lower amounts of flame length for arable improved grassland and higher flame lengths in mountain heath and bog or semi-natural grassland, which is kind of in some of these locations where you might think of places like the Saddleworth Moor fire, where we see these larger scale fires. But what collecting that field data during the 2022 heat wave and other conditions has let us be able to do is look at, if we have more of those hotter, drier periods in heat waves or extreme heat waves that we might see, like in the climate scenarios that were just presented, we could then see a huge increase or a significant increase in the flame lengths, going from, in this case, arable being, say 2 meters all the way up to tens of meters of flame length. As the conditions or the fire weather and the associated attributes change, we then see increases in fire behavior. Now, what that has let us do is then look at, okay, if we see those types of characteristics, how might that affect our electricity networks? How might that affect our energy systems? And how can we prepare for those changes now rather than respond and try to mitigate those changes in the future after they've already occurred? So when we look across these different threats, some of my kind of personal closing considerations or reflections on the climate change risk assessment process is we see a real disparity in evidence base and research depth across hazards. So I've just focused a little bit on fires, and what we'll see, as we look at the literature, as we look at the evidence base across research and other aspects, we see that there's been extensive research, great research done on winds and flooding, but less research done on heat and fires. We also see that updates to standards and methods to quantify research are underway. So there's lots of good efforts through technical societies, working groups, to update standards, assess methods for stress testing, quantification of resilience, what types of metrics should be developed both on a UK scale but also in a global context. But oftentimes these look backwards at the actual observed data that we have and can lag the developments that we need for future climate considerations. We also see key upstream and downstream interdependencies for energy across the sector, as well as with other sectors, highlighting the need to continue to evaluate and investigate the implications of failure in one sector or risks to one sector on the related sectors. And then finally, we see evidence of adaptation actions, great evidence of reporting on those actions, but the mechanisms to actually quantify the progress in the energy sector remain limited. So there's lots of opportunities for further improvement. I will note that these are just some of my own considerations, but I will encourage all of you to check out what the findings and results of CCRA4 the technical report will say, as well as you look to see both how your own research fits in, your own considerations fit in, but what the energy sector as a whole will look like both now and into the future. So thanks so much.
Thank you very much indeed, Daniel. It's really interesting stuff. And again, anybody, if you've got any questions for Daniel, please put them in the Q&A box and we'll come to them at the end of the session. Perfect. So our next speaker is Griff Edwards from the TNEI consultancy group. You there, Griff? Perfect.
Yeah.
So you're going to be talking to us about fragility curves and how we can use them with weather data for asset health.
Yes. Is my presentation working all right?
We can't see your slides yet.
It's showing me some kind of carousel version of it. Sorry.
Are you sharing on the Zoom, yeah?
How about now?
No, we're still not seeing anything.
Sorry. Yeah, there we go. And
yeah, that's perfect. There we go.
Okay, great.
Excellent. Cheers. On you up.
Yeah, great. So I'm going to be sort of trying to give you a quick sort of overview of the concept of fragility curves that are commonly used in resilience and that type of modeling of power systems, which definitely have a connection to meteorology and actually fit in, I think, very well with the themes of the last two presentations. So yeah, just to briefly, so I'm Griff Edwards. I'm a principal consultant in TNEI. So just to give the obligatory sort of message about that we're an independent and specialist energy consultancy, and we provide technical, strategic, environmental, and consenting advice to organizations in the energy sector. I'm part of the data science team, but in reality, I think we tend to be mathematicians, physicists, people with a lot of both domain and mathematical knowledge. So I think sort of quite different to data scientists in the conventional sense. And I think we're also fairly unique in the relationships that we have with academics working in the energy meteorology sphere, really. So yeah, hopefully you'll find this interesting, and we're always interested for new collaborations on innovation projects. So yeah, the main question then that I'll be discussing first is what is this concept of fragility curves? So they are a pretty powerful and increasingly popular tool for modeling individual component failures within power systems resulting from stresses placed on them by various types of high impact and low probability events. And in general, those are weather-related events, which includes wildfires, which is maybe a slightly less direct weather-related events, but definitely in that in that category. So basically, what they provide you is the conditional probability of a failure occurring as a result of a hazard of a particular intensity being experienced by that component. So they can be sort of naturally discrete in time, such as earthquakes, which is where they were first developed, or in the case of something like a wildfire that might last a couple of days potentially, then we sort of discretize that and say at this particular half-hour interval, which is a time step in the model, what was the intensity of hazard, which I think in that case probably this flame height metric that was discussed in the previous speaker, that would probably be a sensible hazard intensity there. And you would say, if you're exposed to that level of hazard for an hour, what is the probability
conditional on that intensity that it would fail during that particular time step. So yeah, the type of events captured, as I mentioned, wildfires or icing on conductors, windstorms, floods, or combinations of those types of events. So we have an example there of the way that tends to work. So the assumption is that when the hazard intensity is below this critical intensity level on the left-hand side, then we say definitely that hazard isn't going to cause it to fail. At the other end, we have a probability of 1. So we say if it's above that, then we know for sure that it's going to fail. And then we have this sort of sigmoid shape in the middle generally, although it can also be linear in some models, sort of describing that increasing probability. I think I've just covered that one already. So yeah, obviously we're interested in particular here in weather-based models. But in reality, to have a fully realistic simulation of these things, we would want to be modeling all of the hazards that might be acting simultaneously. So, for example, we might have high winds impacting on lines that have developed some ice on them, for example. So we're modeling the both in that case. But also, we want to be ensuring that we have a separate fragility curve for each component within the system of interest. So if we're looking at overhead transmission lines, you'd need to have fragility curves for the conductors themselves, the clamps that tie them to the towers themselves, the electrical insulators, all those things. So we need to be representing all of those components at the same time, and of course allowing for the possibility that a failure could happen to any one of them, and also possibly multiple different hazard types at the same time as well. So yeah, going to look at where this concept of fragility curves come from. It's a slightly different context to the weather-based power systems one. So they were initially introduced as a way of modeling the damage caused by earthquakes, actually by the relevant bodies in the United States dealing with those kind of things. And the thing that characterizes it is that there were a number of progressive damage states. And it's the purpose is to understand after an earthquake of a characterized by certain hazard intensity, how many of the buildings, let's say in a village, would be in each one of those successive damage states at the end of it. So, so the reason why these are probabilistic is because there is going to be innately a difference in the quality of the buildings, perhaps the quality of the materials or the craftsmanship in building them and so on. But in general, it's kind of assumed that they're all in a known state, which is this sort of undamaged state that which is deterministic. But because we have this probabilistic representation of the quality of the building, then a deterministic hazard intensity will lead to a probabilistic result. There's a certain probability that it transitions from the initial intact state to one of those progressively worsened damage states at the end, the worst of which is the complete collapse of the system. So these fragility curves in that case simply tells you the probability that it's transitioned from that state to any of the other higher states, higher damage states, and so on. And again, sort of based on the fact that we know for certain what the initial state is. In energy systems, and this is probably one of the main shortcomings, I think, of the fragility concept, is that in general, they only assume two states, which is basically functioning or intact or failed. But of course, in reality, there's going to be lots of different interacting hazards, some of which will be degrading the asset, not causing it to fail. So I think there's definitely a limitation when we're just considering that any particular hazard can only have the effect of either destroying it or not weakening it in some kind of way. So yes, in fitting fragility curves, there's a lot of different approaches, sort of some advanced computational physics-based methods, sort of civil engineering approaches, metallurgy in particular on it, because we're dealing with, of course, metals in the towers and conductors and so on. A lot of other approaches sort of try to find what data was available. I think quite similar to the metaphysics approach you heard about in the first presentation, or others that is based on just the experience and general expert opinion of experts working in the field. And if you have a particularly sophisticated approach, there might be combining those in some sophisticated statistical way. But another shortcoming, I think, of the approach is that it tends to be that once one person has done some study and fitted a curve that might be applicable in one particular country, they're generally taken to be universally applicable for that type of hazard, which is definitely a bit questionable. So yeah, sorry, I've covered that one already. And then a quick note that it tends to be so that this sigmoid shape, and people tend to fit the probability density functions of continuous variables. So probably the most popular being the normal distribution, and that can sometimes lead to some confusion in that people believe that fragility curves are actually cumulative probability functions. That, of course, is not the case. It's what we're really talking about here is a binary variable. It's just that the conditional probability of ending up in the failed state is increasing. So essentially, the properties that you would need of this function match the properties that you need of a probability distribution, which is why they are suitable for use in characterizing them. So I'm just going to very quickly move on to giving an idea of why sequential Monte Carlo simulation is a very essential and centrally important tool in energy systems modeling. So here's maybe a relatively simple example where we might want to sort of do a capacity adequacy assessment. That's basically saying sort of how frequently is it going to be a situation where maybe due to the unfavorable weather conditions and maybe some combinations of faults in thermal generators and so on, that not all of the demand in the system can be supplied. And in general, we're interested in working out what's the expected value of that metric. Or actually, in this case, we're looking at a metric that's not just saying was the energy unserved or not, but actually we're saying how much was the unserved energy as an expectation and over all hourly time steps in the year. And that involves the difference between a bunch of random variables, being the demand, the thermal generation, the intermittent renewable generation, and maybe also the contribution of storage to that balance of supply and demand. Now, of course, the store can only export and support that supplying of demand when most needed if it has filled itself up and if it hasn't already exported that energy when margins were looking tight. So we need simulation to evaluate this slightly complex difference between variables, and it needs to be sequential as well, because obviously the ability of storage to support that depends on what it has done in the last couple of hours, and it has finite energy and power capabilities. I guess so. The nice thing about fragility curves and why they're so popular is how easily they can be integrated into a sequential Monte Carlo simulation framework. So, and it tends to be that within that sequence, so within the simulation, we might have a time series of weather variables. Now that can be either reanalysis data or also the climate change projection time series as well. And then we basically sort of, given those things, we might be working out physical things like perhaps the temperature of the cable, in the case when we're looking at aging due to extreme heat. And we're also then maybe looking at, sort of based on those hourly values, what might be the maximum, let's say 3-second wind gusts and so on. And then we work out what the hazard intensity is on a particular time step, and then we sample based on the probability that the fragility curve tells us. We then sort of sample, did it fail or did it not, with that probability given in that sort of way. So this next one, it doesn't matter to understand the exact details of it, but this is a sort of a framework moving on from just this kind of network-free consideration of adequacy to maybe understanding if there's going to be any, like I said, energy not served or loss of load probability that results from those hazards when we are modeling the network, when we are modeling, given this fault, how would the power flow be changed, and how would things be redispatched, and will there be instances where it's impossible to continue to supply everyone with all their demand without pushing components outside of their limit? So that's the general framework for doing that kind of thing. This is an example where we're considering thermal degradation due to which may be getting more intense as a result of more intense heat waves. And then we're sort of combining that sort of maybe weakened state with the ability to withstand the tension forces that are created by wind gusts. And then again, we in general there we have those time series, and then the fragility curve is in here, and then we end up with these metrics of interest, which is did it lead to any instances of not being able to serve all demand completely? So we're going to look at more closely at some of the limitations of fragility curves, which I've already briefly mentioned. So what really does this curve represent? What does it mean for a curve to be wider or narrower, and so on? Well, really, it's representing the sort of cumulative combined effects of lots of different types of uncertainties that are present. So the more spread out it is, then the more uncertainty is present. And if you're in a completely deterministic situation, the fragility curve just becomes a sort of a step function. Sort of the conditions for failing are there, and the physics then determines that it fails or it doesn't. So yeah, one of the larger sources of that uncertainty, in addition to the perhaps the initial states that we discussed in the case of earthquakes, is also the fact that your nominal hazard intensity, or that is the nominal value of weather variables, is not going to be an exact match to the precise weather conditions that's going to be experienced by individual spans. And that can be also because obviously topographical features can change wind speeds and so on. And of course, because things like reanalysis are these averaged and tend to be more smoothed values compared to the more noisy reality. So one of the examples that we've been working on a project that's an NIA-funded project called Thermal is exactly that combination I was talking about. The slowly, what is the effect of heat waves and windstorms combined? And in that case, we are taking a slightly different approach. Or we're saying sort of where the hazard in that case is simply what was the maximum 3-second gust strength, conditional on the hourly values. And there's a lot of uncertainty around the fact what is the angle of the wind, how does that, what's the relationship between the sort of reanalysis or climate change run compared to the much more localized values and so on. And those kind of uncertainties are very difficult to quantify precisely. So yeah, sort of talking about there. Sorry, I think I've covered that material already. Right, yes. So the problem with the approach, the fragility curve, is that it's a static approach. So not only do we have this problem that we're kind of assuming this universal applicability, but also it's assuming that the same hazard intensity will always have the same, lead to the same probability of failure, regardless of what it's maybe experienced in the recent past. And I think in some ways that this is a problem that's avoided when you take more of a top-down approach, as we heard the Met Office is taking, because it's kind of those true effects where multiple exposures, maybe within one event to a particular hazard, sort of changing the probability is kind of accounted for in what you're observing. Although I think the fragility curves also have a benefit of being this bottom-up approach as well, where we're really sort of trying to understand on an individual basis and based on physics what's happening as well. But yes, it's modeling them as static was in reality that they would definitely have to be modeled as dynamic in some way. And I mentioned again this question that if you assume a certain relationship between, say, a reanalysis data set and the probability of failure, that would depend not only on the sort of general direction of the line, but also on the degree of sort of essentially wobbliness of that direction. Yeah. To what extent do you see individual spans deviating in their direction from the overall direction of the line? Because of the non-linear nature of the impact of wind direction on forces, then it's very difficult to come up with one particular stable representation that accounts for both that sort of general direction and the extent of deviations away from that. So this is more of a sort of stylized representation of how we might be modeled in a more dynamic way. So we see here, for example, with a new conductor, a certain wind speed leads to sort of this sigmoid shape again of the probability of failure. Whereas with an older one, the same wind speed is more likely to has a higher probability of causing a failure because of the weaknesses that might be caused by, for example, exposure to higher temperatures than is that might lead to degrading processes. And a similar thing. And so this one is also looking at, originally there was an idea that even heat waves themselves and their impact through annealing might be modeled through the fragility curve concept. Although I think in that case, the problem of that the probability of failure depends very much on the past is way more applicable. So the sort of the plausibility of treating each one as kind of independent of its past is way more plausible if we're looking at those kind of hazards. Whereas it's definitely a feature, but one that perhaps can be accommodated for in some way in that case. I think I'm going to skip this one because it's a bit too much. So what are some of the ways to get around that? Well, this is, again, this example that we did in this thermal research project with the same structure that we had before, but instead of having a probabilistic fragility curve, the approach that was taken there was that we still take a single, essentially deterministic time series from the climate models or the reanalysis data, but we add some probabilistic component to that. So that might be sort of that we model the current flow through a line as using a generative time series model. So that combines with a deterministic model of air temperature time series to give this probabilistic view of cable temperature, and then an entirely deterministic physics-based model of how that causes degradation. Similarly, with the effects of wind speed, we take the hourly average wind speed as this deterministic time series, but we sample randomly from what the maximum 3-second gust strength might be using a probabilistic model. And then instead of a fragility curve, we again have a deterministic physics-based model of whether the maximum tension forces are greater than its ability to withstand them, given the degradation that's happened due to strong heat. So the conclusions here are that fragility curves are definitely useful, and it's very understandable why they're popular due to their simplicity and the way they naturally fit into sequential Monte Carlo simulations. But as discussed, they have some very serious limitations, which is the fact that they're not as universal as they assume, and that they're certainly not static. And then the example that we've been working on is this way of how to model the combined effect of annealing due to high temperatures, which might be more intense with climate change, with more intense heat waves, and also windstorms that may have higher maximum wind speed. So we've essentially taken away all the stochasticity from the fragility curve concept. But in that approach, we didn't account for any model, or we might say epistemic uncertainty. So we essentially removed the aleatory uncertainty that was built into the fragility curve, removed it, and then just assumed a deterministic result. But I think it would be interesting to do some research on maybe like a third option where it's, I think, correct to remove this kind of baked in aleatory uncertainty because of the fact that it's so different in different contexts, but try to still keep in a probabilistic element, which is trying to capture the epistemic uncertainty involved. I also think it's very interesting to see whether in any future work we might be able to combine the sort of top-down approaches that the Met Office was talking about in its presentation, where we know and using that to calibrate perhaps this more bottom-up approach involving a altered concept of fragility curves, so that we have the calibration, but we also have this much more informed and physics-related view of what's actually going on, what's actually causing those failures. And yeah, thank you very much. That's it.
Thank you very much indeed, Griff. Again, if you've got any comments or questions, please put those down in the chat box at the bottom, and we'll come to those at the end of the session in the Q&A section. So our last speakers today are James. I think it's just you yourself at the moment, isn't it? So it's James from the Met Office, James Fallon. So I can ask you to share your screen, and I'll let you take it away.
Great, thanks, James, and yeah, thanks for inviting me to speak. Paola, unfortunately, isn't able to join today, although she might be able to join at the end of the Q&A, so you might hear from her later. So I'm going to be giving a high-level overview of how we use climate science and weather data in the industry consultancy team in the Met Office, and then talk about our event sets and scenario developments that we've been working on recently. So just a bit about the team. I joined the industry consultancy team over a year ago now, which is a small team, about a dozen or so people that sits within the Met Office. Our purpose is to provide expert scientific integration of weather and climate information and insight into industry processes to support industry in making better decisions, supporting critical activities. For industry, this benefits is to improve safety of operations, increase efficiency, save customer money, aid design criteria, and ensure future resilience and help plan for a net zero future. And benefit for the Met Office for having this team includes providing insight into emerging applications of weather and climate data. We can monitor and discuss with customers what they're working on, how they're developing pioneering scientific applications, and help feed this back in to understand sort of in both ways, what data is needed to support industry and vice versa. We work across all areas of industry, but in particular energy, water and infrastructure. I have a particular focus on the energy sector. And we work across all timescales from past climatology to today's weather, seasonal forecasting, future climate change projections. So we've already had quite a bit of context from all the previous talks, so I won't linger too much on my first few slides. But the plots I've got here, the one on the left is showing you the GB grid past the last few decades, and you can see the change in the energy mix with the phase out of coal, which is shaded in grey, and the rapid emergence of renewable energy is meeting an increasing proportion of our national electricity demand. And on the right is our energy future. So these are pictures, or these are figures of the future energy scenarios developed by NESO, the National Energy System Operator. And this is showing the anticipated level of demand being met under different scenarios. And actually, the scenarios don't look quite so different in terms of the total amount of demand, but they do differ significantly in how that is being met and supported. So when we talk about climate resilience of energy systems, it can be quite helpful to split this thinking into two separate areas. So on the one hand, the security of supply, and that refers to the ability of the energy system to reliably meet demand under all conditions, including during periods of stress or disruption. And on the other hand, there's resilience of energy infrastructure, which refers to, for network and assets, which refers to the ability of electricity and gas networks and assets to anticipate, withstand, and adapt to rapidly recover from a wide range of hazards, which can include extreme weather, climate change, as well as other hazards more broadly beyond weather and climate. That could be cyber threats and system failures. So this can be quite a helpful way of thinking, but it might not always be fair. And we know that the causes of physical failure to assets might be correlated with periods of stressful events, whether that's a peak in demand, a drop in renewables, or a ramping event or otherwise. The timescales that we work with, pretty much anything. And in fact, I think maybe even going beyond what's shown in this slide here, because energy system operator and the distribution network operator will care about even down to the sub-second delivery of power. While there might be some stakeholders in the energy sector and other infrastructure who are thinking even beyond just a few decades, but even into the next century if they're planning for building infrastructure that's got to last for a long time. But we support operations at a variety of scales, second-by-second operations, planning days, weeks, seasons ahead, anticipating infrastructure risk from storms, which can be days ahead, and looking at climate impacts in the years, seasons, and decades ahead, to security of supply and to physical infrastructure hazards. What about spatial scales? So again, we've got to think about a broad range of scales. And just to take one example, I've collected a few infographics from the UK CP18 guidance, as it's quite a nice example. So if we're thinking about climate change data and how we could use it to support the energy sector, in the UK CP18 dataset, there's a choice of 3 different models, and you might use these for quite different purposes. So on the one hand, the global model is helpful for projects that are going to look at high-level impacts, changes to circulation, positions of the storm track, the North Atlantic Oscillation, which describes whether you're going to have sort of milder conditions, wetter conditions, and that kind of thing. And it could be a very useful way of understanding and interpreting the weather for the UK. And then you can look at the regional models if you're more interested, for example, in flooding or pan-European impacts, and you don't quite want to go down to the local model because you need larger area coverage. And then the local model is really useful for looking at short duration events, intense rainfall, anything to do with really convective weather. So they serve quite different purposes. But then if you're thinking about different timescales, different data sets, you might be thinking about the different spatial scales in quite different ways. Another consideration when we're working with weather and climate data and how we might put this into action is the increasing interest in compound events. And I know this is something that distribution network operators are increasingly considering, and that it's written about in the assessment reports that were discussed earlier. So it can be quite helpful to try splitting compound events into different categories. These aren't always a perfect fit, and there can be overlap. These infographics are showing multivariate compound events which co-occur in the same space and time, spatially compounding events which occur in different spaces but at the same time, and temporally compounding or preconditioned events that occur in the same space but over different time steps. And you can come up with other compound events, and there's lots of other ones that have been developed, thinking about multi-hazard compound events and cross-sector compound events as well. Another step that we take when thinking about developing our impact approaches is whether we go for a top-down approach to understanding hazards or bottom-up. So in a top-down approach, we can explore the weather and climate events that impact the system, and we might think about introducing, for example, a threshold and exploring when temperature goes above a certain threshold or below a threshold, and just to, based on that simple measure, just explore what weather events we might expect in the current climate or the future climate. Alternatively, if we're able to begin by understanding physically what's impacting the system and developing an impact model and exploring that before switching to exploring the weather events, that can be a useful alternative approach as well. And there's not always a right answer. It depends really on the problem at hand, what kind of approach you might take. So just going into a bit more detail on that, you could even split down the top-down approach into top-down hazard, as I mentioned before, about introducing thresholds, or you might have a specific impact variable or index in mind, for example, fire weather index. So your first step is to identify what threshold or index you care about, then to assess how likely that this is to occur in current climate, and to, if you're exploring the climate change impacts, you could then move on to looking at climate change data as well. While if you're taking a bottom-up approach, then you'd first begin with identifying impact metrics. For example, you could look at the number of line sag events, which is something that distribution and transmission system operators might care about. You can then calibrate an impact model, verify and bias correct it before applying it to your weather and climate data. So moving on to the second half of my presentation, I'm going to talk about some work that we've been doing within the team recently on developing event sets for trying to simplify how we use weather and climate data. So scenarios and stress testing are commonly used to assess levels of current and future resilience. By design, scenarios are meant as a tool to manage uncertainty and complexity. So when we consider this in the context of weather and climate, we can easily see how this means considering increasing levels of uncertainty and complexity. So it's actually easy to reach a certain level of scenario fatigue if you just bombard whoever wants to use this data with all of these different scenarios, different uncertainty. It can become quite overwhelming. Additionally, these scenarios are often presented, for example, as a reasonable worst case or the most extreme or some other qualifying factor. But worst according to who and for what purpose? Even for a single customer or client, they might care about more than one thing. So worst doesn't really make sense. What might be the worst weather event for one thing might not be so bad for someone else. And then another consideration is the different narrative or quantitative scenarios that are being proposed. So there's a lot of different practices that are available and not a good consensus of what to go for. So we've been exploring developing better scenarios and beginning importantly with expert elicitation, co-production, to really try and narrow down and manage uncertainty and complexity. So we then derive a categorization of events that then lead to the creation of event sets And these are mined for specific desirable characteristics to become scenarios for a given application. So I'm just going to talk through one specific example where we look at the case of windstorm events, which, as you've heard already, are really relevant for the energy sector and are a leading cause of weather-driven interruptions. So in this case of wanting to develop an event set for windstorms, you begin by identifying this particular hazard, and then you can categorize it into subtypes. For example, you might identify storms that have an unusual track bearing, or storms that reach a particularly high threshold, maybe the deepening rate or something else. And then you examine this further, starting with historical event sets. So, for example, recent named storms or a subset of that, or even just the last couple of years. And you look at impacts in affected areas, intensity and duration, temporal evolution, target period, and so on. And once you understand and explored this in historical event sets, you can expand it with larger data sets that you might not have considered before, or future event sets from climate change projections, or some other data set that you have available to you. As an example, we explored the wind severity index, which is a popular metric that can be used to understand the potential impacts of storms to infrastructure. And when we started off with a narrow event set of just named storms that had an unusual track bearing, Storm Arwen was found to be the most severe storm in our data set. But when we expanded it to a wider set of storms that included historic 1979 to 2022 storms, it only ranked 40th in this particular implementation of the wind severity index. If you switch to a different metric, so the storm severity index or some other measure of wind strength that might be defined over different temporal resolutions or spatial resolutions, or be transformed in some other way, perhaps specific to a piece of infrastructure or a specific area, then you could get quite different answers again. So we picked up both that it was really important to consider which metric you're using and if it's really the right one for this purpose or not, and also really important to consider the data set you're using and if it's complete enough to represent all the different kinds of storms you might experience. And that might be a bit how long is a piece of string, depending on the kind of data that you've got available. And this is just a particular example showing Storm Arwen on the left, and then a different storm that was picked out from the historic data set, and you could see had quite different impacts, and could arguably be worse for certain types of infrastructure. So I'll just finish up with the last couple of slides. Recent work by a few members in the industry consultancy team and across the office. They've been putting together a catalogue of recent named storms and showing different storm metrics, impact metrics, for example, looking at deepening rates and that kind of thing. This has recently been published, so if you're interested, please scan the QR code and visit the DOI there at Zenodo. I think it's going to be a really fantastic resource, and it's being developed with the operational meteorologists as well, giving feedback within the Met Office. And I think some of them were quite excited to be able to look through and see, oh yes, I remember that storm, and it's really nice to be able to compare how these all rank with each other. Another shout out before I finish. Hope you don't mind, James, that I'm hijacking this to advertise the Next Generation Energy Climate Modelling 2026 event, which is coming up in June. I think it's going to be announced very soon, so you won't be able to find it on the website yet. But I will be helping to run a session on getting weather and climate data into policy and practice on the 17th and 18th of June. So watch this space.
Thank you very much indeed for that, James. It's really interesting. Yes, I've been to a couple of the Next Gen events. Definitely worth going. So no issues with your advertising strategy there. firstly, thank you to all of our speakers today. It's really good to have that and a very broad range of topics that have been discussed. If I could ask all of our speakers and Sean and Paolo, if she's in as well, to come back into the switch their cameras on and microphones on. I see Colin's been very busy answering questions already from within the Q&A. So if anybody watching, if you've got any questions, please put them in, and we'll put them to them. But I think we'll, as you've already answered, I'll start off with one I've got here then. So this is I guess more related to Colin, Sean, and Daniel, I guess. You both mentioned at various points that monitoring was one of the big things that resilience was based on, and particularly some of the aspects of the data that you need to use to be able to assess resilience. Are there any kind of data that you wish you had from either from the energy sector or from the meteorology sector that would be really useful for the work that either Ofgem or yourselves or CCRA are doing that you don't have, that maybe you wish that in the future we could sort out and start getting? Go on, Sean, you can start that one.
Okay, so thanks very much. So yeah, Sean Wilkinson, Newcastle University. So currently the main one that the DNOs talk about is information about the trees, because it's mainly trees blowing onto the lines, and so more and so that's what a cheap one for them to do. Although there are problems in trimming trees because they don't own the trees. The other thing then is they have this information. So when we're talking about a fragility curve, and Griff talked about it as well, we're talking about a single parameter. And so what we really want to move from is a fragility curve to a fragility surface, whereby you can start to consider things like age, and also then monitoring the outliers. So if you look at that scatter in those fragility curves, what you're trying to do is get that down to a single line. So you could, for example, bring into something like age, and they do a lot of the. I certainly know some have that information, and if you talk to them as well, they say things like, "Oh, that area is not so good because it has this kind of conductor." So asset information is there, and it needs to be collated, and then the weather variable stuff. What would be great is to have a lovely gridded data set of historical wind, like we do for temperature and rainfall. That would be wonderful. And also, while because the Met Office is on here, but there's other people on here as well, people would like both historic and future return periods for storms that we've had. And they would find that, especially for windstorms, they would find that, for their region. Here's my region. What's the 1 in 50 year return period storm look like? What's it likely to look like in the future?
Yeah, that's very, very easy in a static climate. I know climate change makes that
Okay,
very difficult. What was 1 in 50 year this year might not have been 10 years ago. Griff, we'll go to you first, and then Daniel, I see both wanting to answer this, so that's perfectly fine. Griff, yeah.
Yeah, just to respond to that, I think, definitely a I don't know, 3 or 4 or 5 dimensional surface instead of a single curve is definitely necessary for that. The approach we took was to basically say, by sort of taking away all of that, all of the probabilistic aspects, and sort of place them all in the as representing the hazard intensities, each as being probabilistic and developing sort of realistic models to generate those things. And then by having what was the fragility curve be entirely based on physics, that is, we were simulating a particular maximum gust strength, and then saying, okay, is that or isn't it greater than the remaining tensile strength of the cable? So making that entirely physics based. And I think if that has advantages, that you can consider all these different things and just figure out what the correct physics is for that, and it maybe overcomes some of the statistical sort of fitting problems that you get maybe with something so high dimensional, given the amount of data that you have for fitting. So we sort of took that as an example of overcoming that issue in that particular way. But like I said, that's in a way we're taking away the baked in aleatory sort of uncertainty. But we were sort of ignoring the fact that there's still, of course, we assumed that our model that relates hourly average wind speed to these kind of sampled maximum strength was correct in that context. So that was definitely cheating a little bit, just to sort of propose something to move on the debate, I think. So yeah, it'd be interesting to see in future how we would still be working with this multi-dimensional surface that represents your model uncertainty. And I think it's a great topic and needs a lot of research.
Sounds like it needs a lot of data as well.
Yes.
Daniel.
Yeah, I think one thing to highlight, I fully agree with everything that Sean said around data. I think all those would be great things to add to the mix. One thing that has been improving quite a lot is access to the outage data itself, with a number of the DNOs putting that out publicly on their open data portals. So that's definitely much appreciated as driving the field forward. I think one other aspect that we perhaps haven't covered so far that would further complement that is around the restoration and adaptation efforts. So I think while there's good information on the outages themselves, how many crews were going out to respond to an event, what were the associated resources that were contributing to that. In some work that we've done with distribution companies in the States, particularly through the Distribution Resiliency Working Group and IEEE, we've done a lot of analysis around how many crews might you can commit to an event, how that then changes the response. And I think that starts to get at the restoration as opposed to just the failure, the damage, the outage side. So I think that would be a nice complement, the more information we could get around responses to the event itself, and both from a resource and network performance side of things, in addition to the failure, that would further complement the ability to evaluate resilience.
Yeah, and I think that's a very fair point in that, there is a lot of data out there that's either written down in a handbook or on somebody's hard drive from 10 years ago that would be very useful to get into to be able to make these, either make low uncertainties in fragility curves or be able to add data to lower uncertainties in some of the other work as well. Colin?
Yeah, thanks. Completely agree with everything that everyone has been saying. I guess just to add to Daniel's comment about the NAFIR's data being available, and this is all of our research wouldn't be possible without this data being available. So this is really important. Furthermore, to add to like Sean's data requests, I think we don't have a high resolution reanalysis product. We have ERA 5, which is at about a 30-kilometer resolution or something. But to really go into like adaptation strategies at a high resolution, because all these things are applied on a local level, and to be able to predict how these things might affect future evolution of the network, we would need to be able to quantify the vulnerability relationships or fragility curves at high resolutions. So I think having these kind of data sets at high resolutions will be very helpful. Also adding to, I think, what Sean said around tree cutting and so on. I've seen like approaches by groups in the US where they're improving their predictive capability of outages when they know what parts of the network have recently had their vegetation cut back or where things have been managed. So having things like this, like what Griffin was saying with these dynamical fragility and so on, would be really helpful to improving our approaches and so on.
No, that all sounds very sensible and should be easily achievable. I've got a question actually for Jane, and then we'll go. I realise there's an AI question that seems to be getting a lot of traction on the Q&A. I think one thing that Colin's brought up, and that's been kind of brought up in a couple of the talks as well, as being this idea of spatial and this like locality, and the fact that obviously different impacts affect different areas differently. Within the meteorological data, are we seeing large differences in how the UK is going to be impacted in the future with climate change? Is it that we're going to see much different, much more severe things happening in the southeast of England compared to the north of Scotland, or vice versa? Or is it just a matter of we don't have enough data to be able to properly assess that? And if so, are there any methods and things that potentially are going to be able to be helpful in that topic?
Sorry, was that addressed at me, James?
It was, yes.
Yes.
I think you start, but if anyone else wants to chip in after them.
I think maybe, Colin, you'll be able to add to this, because your slides as well, it was really great to point out the differences with the different ensemble members. I think that's one of the key things to communicate with a data set like UKCP18, is that you do have these quite stark contrasting differences when you look at the different ensemble members. You can consider whether it's important to bias correct these different ensemble members, or if you might be erasing some kind of signal. So one question when you interpret data like that is whether these differences are representing something that is realistic. Perhaps there's a different global circulation pattern change that's being represented, and this is a real uncertainty we should be considering, or is there some kind of model error that's been introduced somewhere which is causing it to be, for example, shifted slightly warmer than it should be, or the wind's not as windy as it should be, that kind of thing. So it's really important to be aware of these potential differences. And I think it's a really nice idea when you've got resources to look at other models as well. I know that some CMIP models have been added to more recent releases of UKCP18 to add a comparison. So instead of relying on one single model, you can compare to models developed by other centres and see what the uncertainty looks like when you introduce those as well. In terms of regional uncertainty, definitely. Even if you just look at today's climate, the kind of response curves for some impact variable might differ greatly when you look at different regions. One project I worked on in the past, essentially an electricity demand modelling project. If you try to fit even the north of Scotland versus the south of Scotland, you got a completely different curve, partly because of the different geography, but also they just had different equipment installed in these different locations. So in a way, that's kind of the more crucial thing to get right when you're comparing different regions. Yes, there'll be different weather and different climate change impacts, but also just knowing what infrastructure is there and how much it differs, how old it is, that kind of thing is really important to consider.
No, yeah, that sounds very very much like it does need a kind of a different touch for each different area. So yeah, gonna ask this question from Savo. Is there any tips on how best to involve and bring in other disciplines and expertise, such as economics, social research, engineering, etc., into your development of resilient frameworks? Daniel, you want to thank you for taking that quickly?
I'll kick off with things. A couple ways in which we've done that at University of Birmingham. First is the research group I mentioned. Our Resilient Systems and Climate Action Research Group is by nature interdisciplinary. So with people from the social sciences, from health, I sit in engineering, we're all working together on these research topics. So we're putting ourselves in an environment where naturally there is that opportunity for involvement across the disciplines. So I think that's take place or be part in a research group or with research communities like this one in RMETs that are interdisciplinary is a start. I think another way in which we try to do that is a number of, for instance, the PhD students I supervise, I'll bring in co-supervisors from the other disciplines. And so I think that's just a matter of course. For instance, one of my students doing wildfire research, he has supervisors on fire behavior in the geosciences, and then myself in engineering. So I think if you are a student, try to seek out advice or engagement with other groups. If you're an academic, try to bring those groups together. If you're in industry, I think there's some great places where like in infrastructure operators adaptation forum, where there's different types of sectors that are all brought together as well. But I think resilience is something you can't tackle in a discipline specific isolation. Otherwise, you'll lose a lot of the richness that's gone before. For instance, the fragility curves that are presented have come from a civil engineering space, but are widely applied in an electrical space, power system space. So I think looking across those disciplines is really fundamental to this particular topic.
Yeah. I think that the challenge is that for myself, I mainly work in the space of off-gem funded innovation projects. The NIA, in the past NIC, and now of course the SIF projects. But I think there's a really problematic lack of understanding by the people funding projects and stuff there about just how interdisciplinary this really is, and they'll sort of assume that one consultancy that only has expertise maybe in one area is quite capable of doing it. So yeah, getting the message across that it's really necessary to find these multidisciplinary teams is still frustratingly challenging.
Right. Sean?
Yeah, I think there's 2 points. I think to do this properly, to do impact-based forecasting properly, you've got to talk to the stakeholders, in this case, the infrastructure operators, for 2 reasons. One, to get an insight into the data. So the NAFA's data has got 100 and something fault codes, and they can, different operators interpret them slightly differently because some of them are very similar. Also, things like they'll say if something's in the sun, you'll get 10 times more likely to get a heat-related fault than if it's not got direct sunlight on it. So correct, and also so sort of correcting errors and understanding the data better. Also, then what are the cheap? They talk about low regret adaptations. Again, you get that from the operators. And I think for the social scientists, we have incredibly crude measures of consequence. So the insurance companies, so the fragility curves come from insurance companies and cat models, right? And everything downstream from the hazard they call them is an impact, and they measure that in pounds because they're insurance companies. So that's insurance payouts. I think splitting it into consequences, where we start to understand that different people who are without power for 2 days have totally different experiences. And what do those experiences, what does 255,000 customer minutes lost look like, right? It's just, it doesn't really mean anything except for people sitting in the room going, we should do something about it. Anyway.
Yeah, I do remember speaking to someone from California, and they were discussing if you take it purely on a financial side as to the best way to mitigate climate change, you just don't provide power to the most remote regions because they're the ones that are more likely to have a failure and more likely to cause you to have larger outages in terms of time because they're the harder ones to fix. But yeah. Next question then, is there work quantifying the overall cost of failures and then the cost of sensible mitigations? Anyone want to come in on that one? Go on, John.
Well, if somebody else has got their hand up, I can. So what was it? It was a cost of mitigation. So Griff could probably talk about this a bit more, but there is the cost of the load not served. So there is a financial cost, and it's different for different people. So I think Ofgem are thinking about having that as another metric. And I think the other thing though is I think and I think Colin mentioned this, I think we're a bit also simplistic. So at the moment, quantifying the benefits of an intervention is really immature. Okay. And you can do some stuff, right, but it's incredibly immature. But there's more than one way of actually providing resilience. So, for example, for someone, and that's why talking to the infrastructure operators about adaptations and responses. So, in certain areas like rural areas, providing generators is a good way. It is probably a better way in the short term, and while we're transitioning to net zero, than say upgrading the infrastructure there. So there's all these different, and then like trimming the trees first is a better way of doing certain things in certain areas. So it's having a much more nuanced approach as to how we provide that resilience.
Griff?
Yes. Not that I have the answer about how to do the costing of it, as Sean has said, it's a very immature field. But I think that is maybe the area where what I refer to as some sort of bottom up has value. And obviously, I was using it in a different sense to James in the last presentation. I was using it to mean, let's model what's happening during each hour and at each component, and then sort of seeing what's the aggregate effect, rather than just observing and directly modeling that sort of aggregate effect across all components and across all hours of the event. I think this is the area where this more that individualized view might have more benefits, because of the same what's the word? It probably is necessary to sort of understand exactly what happened and where and so on in that much more granular way as the starting point, I think, to getting a really robust picture of how that's developed. But yeah, so much more research to do to come up with a good methodology.
Nice. And Daniel?
I think this goes back to the previous question on bringing in other disciplines. I think one of the challenges is, a power outage, yes, it has cost from the power outage itself, but then has cascading impacts across, disruption to transport or disruption to heating or cooling that then affects health. And so there's all these related interdependent impacts that need to be considered when you're doing cost. And I think that really is something that requires lots more research and evaluation. I've also dropped into the Q&A some examples where the US has recently been trying to re-quantify this. So there's a long-standing interruption cost estimation calculator utilities use to determine how much is an interruption worth. And it was historically used for reliability, but now recognizing the duration and impact from these extreme weather events has much more impact. They've recently surveyed utilities all over the country to get a better estimate of cost from a resilience perspective. So I think there's initiatives like that going on around the world and in the UK as well, but is definitely a rich field for research and further evaluation.
Perfect. And that is spot on 4 o'clock as well, with the last question that we had there in the Q&A. So thank you very much, everyone. I hope if everyone, again, like to thank our speakers who we've had today. It's very, very good for you to give you your time and do this. And like I say, it's always amazing to me how much of a breadth of conversation we can have on, one simple question of how do we assess how the future energy system needs to be made to make sure that it remains resilient and keeps the lights on for us normal people in the country. So thank you very much for attending. I believe a recording of this will be posted on YouTube later on once it's been uploaded by the Royal Met. Reminder that we do have a second one of these events coming on the 23rd of April. The link is on the RMET's website to sign up to that. And so, so finally, again, thank you very much to our speakers. Thank you very much for attending. And I hope you all have a good evening. So, thank you.
Thanks, James.
Cheers.
James.
Everyone.
Cheers. Thank you very much.
Thanks, James.
Cheers.